This is Neil Patori. I'm going to talk about received power models in this segment. All of our probability of bit error formulas are a function of EB over N naught. Well, how do we get the EB and how do we get the N naught? This segment is going to focus on received power, and power times time is this energy per bit. So that's why we're focusing on received power. We're going to call this C. The first model we're going to talk about is the Friis model. And it's also called, strangely enough, the free space model. And the similarity with Friis and free space is often makes it kind of confusing, so I want to explain explicitly that the model is named after somebody, but it represents the received power in an empty environment. And because the environment is empty, we call it the free space model. And this model simply says that the received power, which is in watts or milliwatts even, but the received power is going to be the transmit power multiplied by the transmit antenna gain multiplied by the receiver antenna gain multiplied by this fraction, the wavelength lambda, divided by 4 pi times r0. R0 is a reference distance, short distance that I'll talk about in a second. And then we're going to multiply by r0 divided by r quantity squared. And you're going to very quickly tell me, hey, why don't you just cross off the r0s? There's no reason to make this more complicated. Couldn't we just write? And yes, you could do that. It would be much simpler, but path length is another way to say distance between the transmitter and receiver. And this part will be kind of a constant, something we can measure at a reference distance. So it's measurable. Contains many constants. And it allows us to kind of abstract that away. Now the Friis model, I'm going to separate this and I'm going to talk about the decibel version. Now in decibels, we're often going to write that something in dB, so here, received power, I'm going to write dBm to specify the units explicitly when I convert something to dBm. So in dBm, it's 10 times log base 10 of the linear version. Implicitly, because I can't take the log base 10 or the log in general of a unit of a value that has units, explicitly what I'm doing here is I'm dividing C by 1 milliwatt in the denominator, and that gets rid of the units in C, and that's why I get the dBm. The dBm stands for decibel compared to 1 milliwatt. When we take the 10 log 10 of C divided by 1 milliwatt, we're taking the 10 log 10 of this expression. All those parts of the expression that were multiplication are now turning into addition when we convert these to dBm. So I'm going to get the transmit power in dBm plus the antenna gains in dBm, in dB. Now, antenna gains don't have units of milliwatts because they are always something that multiplies the true power. The gain is a unitless quantity. So when I take the dB of a unitless quantity, I don't need to refer to 1 milliwatt. I'm referring to 1. And when we refer to 1, we're just talking about regular plain old dB. So then I have the GR in dB, that's 10 log 10 of the received antenna gain. And then when I take the 10 log 10 of this expression, I can bring the exponent down, and instead of 10 log 10 of that expression, I get 20 log base 10. Now, lambda, the wavelength, has a unit of meters. R0 has a unit of meters. So these two units cancel each other out. And so I can see that I can successfully take the log of it. The next thing I'm going to do is I'm going to take down this 2, but I'm also going to flip it around because it makes more sense to me to have the r up top in the fraction. So if I say that this fraction is actually r divided by r0 to the minus 2, then you can see how I take the minus 2 down and I get minus 20 log base 10 of r divided by r0. And as long as I keep the units of my reference distance r0 the same as my path length of r, then these units cancel. Again, this part of the expression is kind of a constant at the reference distance. We're going to call it P0 in dBm. My reference distance, if I take R0 to be something of a distance I can measure the received power, like 1 meter away from the transmitter, or 10 meters away from the transmitter, or if I'm talking about cellular base stations that are transmitting over several kilometers, I might even take R to be 100 meters. And then all of this other dependence is just on the range between the transmitter and receiver. So this is something that you could either determine from your components, like you might have a transmitter and you would measure the transmit power, or you would look at the spec sheet for the transmitter and figure out the transmit power. You would be buying antennas and you could look at the spec sheet for the antennas and figure out the gain at the transmit and receive antennas. And of course you would know the wavelength that you're using, lambda. So you might know these things and plug them in to get P0. You might measure them if you can't, or if you want to know for sure. Okay, so this is our equation now is C in dBm, the received power, is equal to this reference power, P0 in dBm, minus 20 log base 10 of R over R0. What happens when we're not in free space? There are very few things that are in free space. Free space meaning that there's nothing there. So space is a great example of free space. We may also have microwave towers that are communicating between each other. And if both towers are high enough, they might not be interfered with things like trees and buildings. And in that case, those towers would also be considered to have a free space link between them. But for other kinds of communication systems that we rely on, like Wi-Fi, cellular communications, these are all ground-based communication systems that are obstructed by walls and buildings and trees and terrain variation. And in those cases, the free space model is not very accurate. The power decays faster than that because the leaves and the building materials actually obstruct our signal. They absorb some of our signal. They transmit some of the signal, but with some loss. So we don't get the same amount of power at the receiver in the real world. And that's where we end up having a different model. And there are lots of different models depending on how accurate you want to be, how much information about the particular environment you have. We're going to talk about this model called the path loss exponent model, which allows me to get a much more realistic model into your calculations without too much complexity. And the path loss model just says that you may have free space path loss up until some reference distance, but after that, you're pretty much going to experience heavier losses as a function of distance. And these losses, instead of being proportional to R naught over R squared, we're going to move towards a model where these losses are to some different exponent. We're going to call that exponent NP for path loss exponent. The Rice book just calls it lowercase n, but I don't want to be confused with all the other times that we use the lowercase n. So I'm using n sub p for that path loss exponent. And in this case, our model simply becomes that our received power in milliwatts, or dBm, is the reference path loss, or sorry, the reference power in dBm, minus, instead of 20 times log base 10 of r over r naught, it's going to be 10 times np times log base 10 of r over r naught. And that np value is going to be typically in the range from like 2 to 4, with some exceptions. Sometimes you'll see a path loss exponent less than 2. Sometimes you'll see a path loss exponent more than 4. Um, but for most land-based communication systems, like cellular communication systems, you'll see an n in the range from 2 to 4. This is just an average. So if I plot log distance versus received power, C, is going to go down because I have a minus 10 np log 10 r over r naught. Okay, so this is going to start at some power p0 when this log is equal to, when the ratio is 1, the log of that 1 will be 0, so I'll get 0 over here. After this, it will go down linearly. And the actual measured powers in this situation won't exactly be on this line. I'll get measurements that will be, around this line. If I measure lots of different received powers at the, different positions in space and I measure how far apart they are, I get something like this, where these variations, these errors in the model might be 10 or 20 or even 30 dB. They're typically Gaussian, so you can kind of imagine this Gaussian distribution around this line. People do measurements of this, and they figure out what NP is for particular environments. NP is going to be higher in dense cities like Manhattan versus University City. They're going to be even lower in rural areas where there are fewer buildings. They're going to be higher when we have terrain variation. If we move our antennas closer to the ground, like for mobile to mobile communications, then I would see a higher value of n than if I put one or both of the ends of the link up in the air, like at 10 or 20 meters. If you wanted to know for your environment how to set this value, you'd either have to look it up in a book where somebody else has done the measurements, or you have to measure it on your own if you're talking about building a communication system for a new environment. Okay, I'll just say that the equivalent linear version of this formula is that instead of the r0 over r squared, we're going to have this fraction to the np exponent. This provides a simple way to get to that. I will also say that the other way that we account for losses in our model is that in the dB version, we subtract some other losses. And in the linear version, we divide by the loss. If I have a loss of 3 dB because of rain, for example, I would convert 3 dB to linear terms. 3 dB is a factor of 2. So I would have 1/2 here in the linear formula. So when our problem statement says you need to account for this loss because it may happen, then I would use that dBm loss or that linear loss to compute the received power. Finally, for wired links, we'll have one more type of model, and this is a model of linear loss. The received power is going to be equal to the transmit power divided by this loss factor per meter multiplied by the length, the number of meters. This becomes unitless. We divide our transmit power by that. Or equivalently, in dB, we'd have C of dBm be equal to the transmit power in dBm minus this loss factor in dBm. That's loss of 1 meter, in dB per meter, multiplied by R. So these two multiply together to compute the loss in the cable of length R. And R is the path length again, and L1M is just our loss per meter. And that's the end of our third model.